Hello everyone, in this video we will learn about the pulley joint and joint components. The pulley joint connects to rigid bodies, simulating the movement and behavior of a pulley system connected by ropes or chains in reality. It achieves force transmission, direction change, and restricts the relative motion between connected rigid bodies. When the triangular rigid body rises, the other rectangular rigid body descends. The dragging of the triangle in the animation is not a function of the pulley joint itself, but an added mouse joint component. This video only introduces the unique properties of the pulley joint. Other properties have been explained in the Joint Common Functions section. The unique properties of this joint are self-ground point, other ground point, and ratio. The term ground point is a direct translation from the box to the engine and not the literal meaning of ground. It represents a stationary fixed point, equivalent to the pulley support in a pulley system. In a pulley joint, there are two pulley supports. One is the self-ground point connecting to the anchor point of its own rigid body, and the other is the other ground point connecting to the anchor point of the other rigid body. When one side of the rigid body moves, the other side moves in relation based on the connected rope, with the movement constraint being the ground point. Initially, the ground point and anchor point are aligned. In the default state, objects of the same mass are stationary. If you adjust the position of the ground point so that it's no longer aligned, the rigid body will move due to gravity. The ratio simulates the principle of motion in real pulley systems. It defines the ratio of change in rope length between the two connected rigid bodies. In other words, there is a fixed ratio relationship between the distance moved by the self-rigid body, the distance moved by the other rigid body. For example, if the ratio is set to 2, it means that when the self-rigid body rises 1 meter on its pulley, the other rigid body's pulley will descend to meters. Similarly, when the other rigid body rises to meters, the self-rigid body will descend 1 meter. Therefore, at the same time, the distance moved by the other rigid body is the distance moved by the self-rigid body multiplied by the ratio. The distance moved by the self-rigid body is the distance moved by the other rigid body divided by the ratio. These three sets of rigid bodies have ratios of 0.5, 1, and 2 respectively, with 1 being the default ratio. Run to see the effect, and you'll find that the movement of the rigid bodies conforms to the properties just described. That's all for this section. Thank you everyone.